The most dangerous number in cosmology is not the age of the universe. It is not the size of the observable cosmos. It is not the distance to the first galaxies, or the mass of the largest black holes, or the moment when the first stars began to burn. It is a number that looks almost harmless, the rate at which space itself is expanding. For decades, cosmologists believed this number was finally under control. They had built a model of the universe that could describe the afterglow of the Big Bang, the growth of galaxies, the spread of dark matter, the acceleration driven by dark energy, and the large-scale structure of everything we can see. The model was not perfect. No serious model ever is, but it worked with a precision that made it feel almost inevitable. Then the measurements became better, and the better they became, the less they agreed. One path into the problem begins near the beginning of time. The European Space Agency's Planck satellite mapped the cosmic microwave background, the faint radiation left over from when the universe was only about 380,000 years old. That map is not just a picture. It is a fingerprint of the early cosmos, its density, its temperature fluctuations, its matter content, and the tiny variations that would later grow into galaxies. If you take that early universe fingerprint, place it inside the standard cosmological model, and run the equations forward for nearly 14 billion years, you get a prediction for how fast the universe should be expanding today. The answer is about 67 kilometers per second per megaparsec. That phrase sounds technical, but the idea is simple. For every megaparsec of distance, about 3.26 million light-years, galaxies should appear to recede faster by roughly 67 kilometers per second. It is a clean prediction. It comes from the oldest light we can observe, and the error bars are small. What makes this so powerful is that the cosmic microwave background is not measured in isolation. It is checked against the pattern of matter across the universe, against the proportions of hydrogen and helium made in the first minutes, against the way gravity gathered galaxies into filaments and voids. The number near 67 is not floating by itself. It is tied to an entire cosmic history. That is why changing it is difficult. But there is another way to measure the same universe. Instead of beginning with the cosmic microwave background and calculating forward, astronomers can begin nearby and climb outward. This is the cosmic distance ladder. It starts with stars whose true brightness can be inferred, compares that true brightness to how bright they look from Earth, and uses the difference to calculate distance. Among the most important of these stars are Cepheid variables. They pulse in a regular pattern, and that pulse is tied to their intrinsic luminosity. Measure the rhythm, and you can estimate the distance. Use Cepheids to calibrate Type 1a supernovae, which can be seen much farther away, and the latter reaches deep into the nearby universe. Adam Riess and the SH0ES team have used this method to measure the expansion rate directly. Their number is not 67. It is closer to 73. 6 kilometers per second per megaparsec does not sound like a crisis. In everyday life, it would be a rounding issue. In precision cosmology, it is a fracture, because both numbers are not casual estimates. They come from careful teams, independent instruments, and years of calibration. The early universe method says one thing, the local universe says another, and the gap is too large to wave away as noise. This disagreement is now known as the Hubble tension. At first, the simplest explanation was that one side had missed a systematic error. That is usually how science repairs itself. Before you rewrite physics, you check the ruler. You check the camera. You check the assumptions hidden inside the measurement. For the distance ladder, one of the prime suspects was stellar crowding. Cepheids live in galaxies. Galaxies are not empty laboratories. They are messy, dusty, crowded fields of stars. If a telescope cannot separate one star from its neighbors cleanly enough, the light can blend together. A Cepheid can appear brighter than it really is. If it appears too bright, it seems closer than it really is. And if the galaxies are calculated to be too close, the expansion rate can be pushed too high. That was the escape route. Maybe Hubble had been fooled by crowded star fields. Then James Webb entered the story. Webb was built for infrared precision. Its mirror is larger than Hubble's. Its instruments see through dust in ways optical telescopes cannot. Its position in space and its sensitivity allow it to separate crowded stellar populations with extraordinary clarity. If the high value of the Hubble constant came from blended Cepheids, Webb should reveal it. The Cepheids should shift. The distances should change. The local expansion rate should relax downward toward the value predicted from the early universe. But Webb did not rescue the model in that way. In Riess's 2024 JWST analysis, the new observations strongly rejected the idea that hidden crowding in Hubble's Cepheid measurements was the cause of the tension. Webb looked at more than 1,000 Cepheids across key distance ladder galaxies and found that the Hubble measurements held up. The ladder did not collapse. The tension remained. This is why the problem became so unsettling. A disagreement caused by a flawed instrument is frustrating, but normal. A disagreement that survives better instruments is different. It begins to suggest that the universe may be telling us something the model is not built to hear. Still, the story is not as simple as one team being right and the other being wrong. Wendy Friedman and the Chicago Carnegie Hubble program have been building an independent route through the same territory. Their work does not rely only on Cepheids. It also uses the tip of the red giant branch and a newer method based on carbon-rich J-region asymptotic giant branch stars. With JWST, those methods have become sharper, and their results complicate the narrative. Friedman's 2024 status report found that the TRGB and JAGB methods land closer to the lower expansion rate, while the Cepheid method remains higher. When combined, the result sits between the two camps, nearer to 70 kilometers per second per megaparsec. That does not make the crisis vanish. It changes the shape of it. It suggests there may be a tension not only between the early universe and the late universe, but inside the latter itself. Cepheids, red giants, and carbon-rich stars are all trying to measure distance. They are all powerful tools. But they do not yet tell exactly the same story. The difference between these methods is not cosmetic. Cepheids are young, bright, pulsing stars, often found in crowded, dusty regions where new stars are born. Red giant branch stars belong to older populations and can be measured in cleaner parts of galaxies. JAGB stars offer another route through the infrared, where Webb is especially strong. Each method has advantages. Each method has weaknesses. Each method looks at a different stellar population and carries a different set of astrophysical assumptions. So cosmology is left with two uncomfortable possibilities. Either there are still hidden systematics in the local measurements, subtle enough to survive the first wave of JWST tests, or the standard model is missing physics. The second possibility is the one that makes the room go quiet. Because the standard model of cosmology, lambda cold dark matter, is one of the most successful frameworks in modern science. It says the universe is dominated by dark energy and dark matter, with ordinary atoms making up only a small fraction of the whole. It explains the cosmic microwave background. It explains the web-like distribution of galaxies. It explains why the universe looks so smooth on large scales and so structured on smaller ones. But success does not make a theory final. Newton's gravity worked brilliantly until Mercury's orbit and the speed of light revealed a deeper layer. Classical physics worked until black-body radiation, atoms, and the photoelectric effect forced quantum mechanics into existence. Physics does not usually break by failing everywhere at once. It breaks first at the edges. The Hubble tension may be one of those edges. One proposed solution is early dark energy. The idea is that, shortly after the Big Bang, there may have been a temporary extra component of energy in the universe. It would have altered the expansion history before fading away, leaving only an imprint in the numbers we measure today. If such a field existed, it could shift the early universe prediction upward, reducing the gap between Planck and the local distance ladder. But early dark energy is not a magic patch. It must solve the Hubble tension, without damaging the many other things the Standard Model already gets right. It must fit galaxy clustering. It must fit the cosmic microwave background. It must fit nucleosynthesis, gravitational lensing, and the growth of structure. Every new idea has to pass through a narrow gate. That is what makes the tension so stubborn. The universe is not giving one clean contradiction. It is giving a contradiction surrounded by successful predictions. There are other proposals, too. Some physicists have explored interactions in the dark sector, extra-relativistic particles, modified gravity, or an evolving form of dark energy. Each idea is tempting for a moment. Then the data close in. A theory that fixes one number while breaking three others is not a solution. It is a trade. Then Webb added a second kind of pressure, not from the expansion rate, but from the distant past. Almost as soon as JWST began looking into the early universe, astronomers found galaxies that looked too developed for their age. Some appeared only a few 100 million years after the Big Bang, yet they were bright, structured, and in some cases surprisingly massive. Before Webb, the early universe was expected to look dimmer and rougher. The first galaxies should have been small, irregular, and still assembling themselves from gas and dark matter. Webb did find many such objects, but it also found systems that seemed to have grown quickly, perhaps too quickly. The most famous examples triggered headlines about cosmology being broken. The truth is more careful and more interesting. Some early candidates were probably overestimated. In the first rush of discovery, brightness was sometimes interpreted as stellar mass, but Webb is revealing that many compact red sources in the early universe may be powered partly by growing black holes. If a black hole is feeding at the center of a young galaxy, it can add enormous light. From billions of light years away, that light can masquerade as stars. This is the mystery of the little red dots. They are compact. They are faint and red. They appear in large numbers in Webb images of the early universe. They may be active galactic nuclei, extremely dense star-forming systems, black holes wrapped in gas, or something that does not fit neatly into the categories astronomers had before Webb opened this window. When black hole contamination is accounted for, some of the early galaxy crisis softens. The most extreme objects no longer require every available atom in a dark matter halo to turn into stars with impossible efficiency. But the problem does not disappear completely. Even after corrections, the early universe still seems busy. It forms galaxies fast. It forms black holes fast. It produces bright systems at times when older models expected less activity. Webb is not saying the Standard Model is dead. It is saying the early universe was more efficient, more complicated, and more violent than our simplified expectations allowed. That distinction matters. A broken model is one thing. An incomplete model is another. Lambda-cold dark matter may still be the broad architecture, but the recipes inside that architecture, how gas cools, how stars ignite, how feedback works, how black holes grow, may need serious revision. And then there is JADES-GS-Z14-0. This galaxy was observed at a redshift around 14, meaning we see it as it existed roughly 290 million years after the Big Bang. That is not long in cosmic terms. The universe was only about 2% of its current age. Yet the galaxy is luminous. It is not merely a tiny spark. It appears large and bright enough to force theorists to ask how star formation became so productive so early. Again, this does not automatically destroy cosmology. It does something subtler. It compresses the timeline. The first stars had to form. They had to live and die. Heavy elements had to be forged. Gas had to cool. Gravity had to gather matter into halos. Those halos had to build galaxies. Some galaxies had to become bright enough for Webb to see across more than 13 billion years of expanding space. Every step takes time. Webb keeps finding evidence that the steps may have happened faster than expected. That is why the telescope feels less like a camera and more like a stress test. It is testing the distance ladder. It is testing the growth of galaxies. It is testing black hole formation. It is testing the assumption that the early universe was slow, simple, and faint. The most important thing to understand is that science is not embarrassed by this. This is the process working at full power. A theory makes predictions. New instruments look harder. The predictions survive, bend, or fail. The surviving parts become stronger. The failing parts point toward something new. Webb has not given cosmology one final answer. It has given it a better set of questions. Why does the local universe expand faster than the early universe prediction? Why do different rungs of the distance ladder still pull toward different answers? Why are compact red objects so common in the early universe? How did black holes grow so massive so quickly? How did galaxies become bright so soon after the Big Bang? And most importantly, are these separate puzzles, or are they symptoms of one deeper missing principle? That is the possibility that makes the story so powerful. The Hubble tension and the early galaxy problem may have nothing to do with each other. One may be about local distance calibration. The other may be about star formation and black holes. They may live in different boxes, but they both appear at the boundary where old confidence meets new data. They both sharpen when the measurements improve. They both force cosmologists to ask whether the universe has been simplified too aggressively inside our equations. The Standard Model assumes dark energy behaves like a cosmological constant, steady, smooth, and unchanging. It assumes dark matter is cold and mostly interacts through gravity. It assumes the ingredients of the universe follow a particular expansion history from the hot Big Bang to today. Those assumptions work remarkably well, but if any one of them is slightly wrong, the effects may not appear everywhere. They may show up as a mismatch in the expansion rate, or as unexpectedly early structure, or as a population of objects that sit between galaxies and black holes. This is why careful scientists avoid declaring victory too early. There is still room for measurement bias. There is still room for astrophysical messiness, dust, crowding, metallicity, calibration, selection effects, black hole light, star formation history, and gravitational lensing can all twist observations in subtle ways. But there is also room for discovery. The safest conclusion is not that the universe is broken. The safest conclusion is that our picture of it is unfinished. That unfinished picture matters because cosmology is not only about distant galaxies. It is the framework that tells us what kind of universe we live in. It tells us whether space will keep expanding forever, whether dark energy is constant or evolving, whether matter gathered under gravity exactly as predicted, and whether the same laws that operate in our laboratories also describe the first moments after the Big Bang. And that is more exciting, because the history of physics is not a history of models being thrown away completely. It is a history of models being placed inside larger truths. Earth was not the center of the cosmos, but planetary motion did not become meaningless. Newton was not the final word on gravity, but bridges and spacecraft still obey his equations most of the time. Einstein did not erase Newton. He explained when Newton works and why it eventually fails. The same may happen here. Lambda cold dark matter may remain the effective theory of the large-scale universe, while a deeper layer explains why the expansion rate is difficult to reconcile, why early structures grew so efficiently, and why Webb sees a young cosmos that looks surprisingly mature. Or the tension may eventually shrink. Future JWST programs may refine the distance ladder. The Roman Space Telescope will survey huge regions of the sky with infrared precision. Euclid will map cosmic structure and dark energy across billions of galaxies. Ground-based observatories will sharpen supernova calibration, gravitational lensing, and baryon acoustic oscillation measurements. The next decade will not rely on one telescope or one method. It will be a collision of methods. Cephoids against red giants, supernovae against gravitational waves, cosmic microwave background against galaxy clustering, Webb deep fields against simulations, black hole physics against stellar population models. If the discrepancy is an error, the net will tighten around it. If it is new physics, the net will make it harder to ignore. That is where the story stands now. Not with proof that the universe is impossible, not with proof that the standard model is dead, but with a set of measurements that refuse to settle into the expected shape. The most profound discoveries often begin this way, not with a dramatic explosion, but with a number that will not move, a small mismatch, a stubborn residual, a line on a graph that refuses to pass through the point where theory says it should. For cosmology, that number is still waiting. The early universe says the expansion rate should be near 67. The Cepheid supernova ladder says it is closer to 73. Other stellar methods pull the answer toward the middle. And Webb, instead of ending the argument, has made it sharper. It has removed some excuses. It has added new mysteries. It has shown us galaxies and black holes closer to the cosmic dawn than anyone expected to study in such detail. The telescope did not simply look farther away. It looked back into the assumptions. And that is why this moment matters. Because if the model survives, it will survive stronger, with better calibrations and deeper astrophysics. If it fails, it may lead to the next great expansion of our understanding. Either outcome changes the story. For now, the universe has not answered with a sentence. It has answered with attention. And sometimes, in science, attention is the first sound of a door opening.